So Marie Curie focused her work on discovering different radioactive elements, but Ernest Rutherford and several others were working on characterizing the radioactivity itself. What is this thing that's being emitted and causing the photographic paper to darken? So we now know that it's the nuclei of radioactive elements that are unstable. They're going to decompose and they're going to shoot out small particles. Why do they do this? They do this to become more stable. There are different categories of radiation. There's alpha decay, beta decay, gamma ray emission, positron emission, and electron capture. And we'll talk about each of those. See, they started using the Greek alphabet, alpha, beta, gamma, and then I don't know what happened. So we learned about nuclear symbols back in Chem 1A, and we're going to use these again, so we'll review them quickly. A nuclear symbol consists of the chemical symbol for the element, that's the same one that's on the periodic table, C for carbon, Cu for copper. And then we have a superscript and a subscript to the left of that symbol. At the top is the mass number, and at the bottom is the atomic number. The atomic number is the number of protons. That's the number on the periodic table. So you look at carbon, and it says 6. Carbon has 6 protons. Its atomic number is 6. What's its mass number? Well, the mass number is going to be different for different isotopes of carbon. The mass number is the sum of the protons and the neutrons. Those are the particles that have mass. Electrons are so small, we can essentially think of them as not having any mass. So the mass number, the big one goes on top, the small one goes on the bottom. If we want to know the number of neutrons, we take the mass number and we subtract the atomic number. So it's like this is all stacked up for us to do, subtraction, right? A minus Z is N. Most elements do have several different isotopes. We learned about those also in Chem 1A. And you cannot tell which ones there are just by looking at the periodic table. When we're referring to a particular isotope of an element, we'll often call it a nuclide. So a nuclide is one specific isotope of a given element. So we can represent those nuclides with their nuclear symbols that we just looked at. We can also represent them using the element name or the symbol followed by a mass number. So carbon-14, for instance, that's its nuclear symbol, has 6 protons. You could also call this C14 or carbon-14. The 14, the mass number, is the important thing because we can always find the atomic number of carbon. It's on the periodic table, right? We need to know what the atomic number is for this specific nuclide. When we're talking about those subatomic particles that come out of the nuclei, we can also represent those with nuclear symbols. So here, a proton. These have lowercase letters because they're not elements. So P for proton, N for neutron, E for electron. A proton has a mass number of 1 and contains 1 proton, right? A neutron has a mass of 1 and contains 0 protons. So 1 and 0. And the electron has a mass of 0 and the number of protons of -1. We'll get to that. So the first type is alpha decay. So in alpha decay, an alpha particle is given off. Yeah, that's That's real helpful. So this is the alpha particle. An alpha particle is a helium nucleus. This has a total mass number of 4. It's got 2 protons and 2 neutrons. So it is identical to a helium nucleus, but there's no electrons. So is it helium? You could argue about that. It's just the nucleus. So that's the alpha particle. So here we have this unstable nucleus, and it's just like, okay, and it spits this particle off. So 2 protons, 2 neutrons together go flying away. And that's alpha emission. And this is what Schrodinger was talking about in the experiment with the cat in the box, with the radioactive element that is either decomposing or not decomposing, right?
I'm sorry he ever had to.
Yeah. So we can write a nuclear equation to represent what's going on here. The basic idea is the same as with a regular chemical equation. But now we're going to keep track of the mass numbers and the atomic numbers. So the mass numbers on both sides have to add up to the same number. So on this one, we've got 238 total. Over here, we have 4 plus 234. That adds up. And the atomic numbers, 92. Down here, we have 90, and we have 2. These are basically telling us how many neutrons and protons there are in this thing, right? And so they need to be accounted for. So we talk about the reactant as being the parent nuclide, and the parent divides and produces a daughter. Why not a son? I don't know. This is the daughter nuclide. And then this is the radiation. So the very different thing about nuclear equations is the elements are changing what they are. Remember, until now we've been saying, carbon is carbon and it's not going to change into anything else. You can rearrange things, but it's not going to change into anything else, except in nuclear chemistry. This is nuclear chemistry. Okay. So carbon can turn into something else. And uranium can turn into thorium, and it does all the time. Okay? So we're not balancing element symbols here. We're balancing mass numbers and atomic numbers. So we should be able to do something like this, right? The nuclear equation for the alpha decay of PO216. PO is polonium. You can do this even if you don't know what polonium is. We do need to know what alpha decay is. So alpha decay is a helium nucleus. Alpha decay means an alpha particle is coming out of this thing. So this is what we're starting with. This is the element symbol and the mass number. So we've got Po, 216, and we look up the atomic number on the periodic table. So Po's over there is number 84. 84 protons. That didn't look much like a 4. So that's the parent, and it's going to decompose into something plus this alpha particle. They always put the daughter first instead of the alpha particle. I don't know why. So how do we figure out what that is? We fill in the missing numbers first. So over here, I have 216 in the superscripts, the atomic numbers. Over here, I've got something, I don't know what this is, and I have 4. So I'm asking myself, what plus 4 equals 216? 212. So this is going to be 212. And then on the bottom, total of 84, what plus 2 equals 84? 82. It's okay to use a calculator. I want to get it right. So 82, we look in the periodic table, find 82, and that's lead. So this is Pb. That's it. Okay with that? Maybe seems a little too easy compared to some of this other stuff we've been doing. That's all it is. So some information about alpha decay. So you do need to understand relative powers of alpha, beta, and gamma radiation. So they give an analogy in terms of vehicles. They talk about an 18-wheeler truck, semi-truck, and a car and a motorbike. So alpha radiation is the semi-truck of radioactivity. It's big, right? It's a helium nucleus. It's big. And so it has high ionizing power. Ionizing power is the ability of the radiation to ionize molecules of another atom. So this particle hits another atom and causes it to lose electrons. So this is a thing that's just, blasting, right? It's just running into stuff. Very effective at doing that. Ionization is bad because in a living organism, it'll disrupt the chemical reactions that are causing the life to keep going, right? Because an ion is not going to undergo the same chemical reactions as a molecule. So ionizing power is dangerous to living organisms. Alpha radiation has the lowest penetrating power, which means the ability to go through things. I don't think we have a picture. I guess, I've just had this picture in my head and it was so vivid I thought there was a real picture. So picture with me a traffic jam. Okay? It could be on an LA freeway, it could be a downtown New York street, anywhere. Traffic jam, right? Gridlock. You got a semi-truck in there. Is the semi-truck going to have trouble moving through that traffic jam? Heck yeah. Real tough to switch lanes. He's just kind of stuck, right? The big, bulky guy. So penetrating power is the ability of radiation to penetrate matter, to go through matter. Alpha particles don't go through matter very well. Alpha particles can be stopped by a piece of paper. Even a fair amount of air will stop them. A t-shirt, right? It's going to stop it. So, in order for radiation to damage living things, it has to get into the cell. Alpha radiation has a hard time getting into the cell, right? It's not going to come in through your skin. What is very dangerous about it, though, is if it's ingested or inhaled. If you eat it or breathe it in, now it's gotten into your body and it has access to various cells. The alpha particles could damage your skin, but your skin regenerates itself, right? And it's got multiple layers, so it's not going to get any further than that. The next type of radiation is beta decay. So here, an unstable nucleus emits an electron. What sounds wrong about that? What are in the nucleus? Protons and neutrons. So how can this thing that's protons and neutrons emit an electron? Right? So what happens here is that a neutron changes into a proton and an electron. I'm not making this stuff up. So we can write that like this. The neutron turns into a proton plus an electron. And now we can understand why this is a -1. It's to make the math work out. Because the atomic numbers have to add up to be the same. Well, proton has an atomic number of 1, and a neutron has an atomic number of 0. So how do we get this side to be 0? We give the electron a -1. I know, seems a little fishy, doesn't it? So beta decay, you've got your parent nuclide decomposing into the daughter and emitting this beta particle. So that's the symbol for the beta particle. A beta particle is an electron. So what's happening here in the nucleus is that one of these neutrons turns into a proton, and when it does that, it spits out an electron. So in Chem 1A, we pretended that protons, neutrons, and electrons were like the smallest things there could be, right? The proton, I mean, there's nothing inside of a proton, right? Well, wrong. There's all these other particles and stuff. I know. Particle physics. Not my thing. This is enough for me. But so just go with me here. A proton can turn into a neutron and an electron. I know it's disturbing. So in our traffic analogy, beta radiation would be like a 4-door sedan. Less massive than the alpha particle semi-truck. So the ionizing power, its ability to damage the molecules in an organism is less because it's smaller, right? But its penetrating power is greater because a 4-door sedan in that traffic jam has a much better chance of negotiating its way through ahead of the semi-truck, right? So beta radiation can be stopped by a sheet of metal, a thick piece of wood. So this is more dangerous outside your body because it can go through your skin and get into other parts of your body. So it's more dangerous outside your body than alpha radiation is, but it's less dangerous than alpha radiation if it's ingested because it has lower ionizing power. Gamma ray emission. So this is not actually a particle in the sense that electrons and helium nuclei are particles. So this is electromagnetic radiation. Basically, these things are high energy photons. So the gamma ray has no charge and no mass number. So when a gamma ray is emitted, the mass number and the atomic number of that nuclide do not change. The symbol for it is the Greek letter gamma and 00. So there's not going to be a question where we say, write the nuclear equation for the gamma ray emission of such and such. I mean, there's not really anything to write. It's just this plus the same thing plus 0, right? This usually happens with other types of radiation. So here's an example. What kind of particle is this guy right here? Alpha particle. So this is alpha decay of uranium-238. It emits an alpha particle and a gamma ray. And you're not required to memorize these things, right? We'll give you the information you would need to write an equation, say. So gamma rays are like motorbikes or motorcycles. So they have the lowest ionizing power, right? So if you think about maybe, I know this is where my picture was coming from. If you think about the molecules in your cells as being like brick walls, right? Semi-truck comes in and hits the brick wall. Does it do damage? Yeah, it does lots of damage. How about a 4-door sedan? That can do some damage to a brick wall, right? What about a motorbike? Not so much, right? So gamma rays have the lowest ionizing power. But think about them in the traffic jam. A motorbike can actually go between stopped cars and get all over the place, right? You might get a ticket if you do that, but you can do it. So gamma rays have high penetrating power. So it takes several inches of lead, like inches of lead, to stop it, or big, thick slabs of concrete. Goes through pretty much anything. Positron emission. So positron, this word is a little bit like electron, right? They both end in tron. A positron is the antiparticle of the electron. Matter and antimatter are a real thing. It's not just in science fiction movies. So if a positron collides with an electron, a particle and its antiparticle collide, they annihilate each other. They're both gone. And they release gamma rays. So in positron emission, what happens is that a proton is converted into a neutron and emits a positron. So this is the positron. It has is very much like the electron, right? But it's positive instead of negative. So in beta decay, we were looking at a neutron turning into a proton plus an electron. So we had and this is the antiparticle, and it's just kind of opposite. You see that? So here we've got a proton changing into a neutron and emitting this positron. So if you emit a positron, then the atomic number decreases by 1. Because a proton got turned into a neutron. So there are fewer protons. Positrons, being the antiparticle of an electron, are very similar to electrons to beta particles in ionizing and penetrating power. They'd also be four-door sedans, maybe a different color. This one's a little different because instead of something shooting out, something's getting caught. Electron capture. A nucleus is assimilating an electron from one of those inner orbitals of its electron cloud, maybe a 1s electron, sucked into the nucleus. So the particle gets absorbed instead of being emitted. And so the net effect is the reverse of beta emission, right? So we have a proton and we've got this absorbed electron, and that's forming a neutron. So when this happens, the atomic number also decreases by 1. But this is absorbed, so it's a reactant. So this table in your textbook is just kind of summarizing these different things. So what do you need to know? That's a good question, right? What do I have to know about this? You need to know the symbols for these. So that if you were asked to write a nuclear equation and told what kind of radiation was happening, you could write a balanced nuclear equation. You should also know the relative ionizing and penetrating powers. Okay. Alpha particles, the semi-truck, has the most ionizing power to damage molecules, least penetrating power. Electrons, the beta emission, and the positrons are in the middle, and the gamma rays are at the bottom. Very little ionizing power, but tremendous penetrating power, the motorbike. So let's practice writing some nuclear equations. So this is asking us to write 3 nuclear equations representing the nuclear decay sequence that begins with the alpha decay of uranium-235, and then followed by beta decay of that daughter, and then alpha decay. So here's what we're starting with, uranium-235. So uranium-235, and we need the atomic number of that guy, 92. So the first thing is alpha decay. So we're going to end up with something plus an alpha particle, which is the helium, 4-2. So total's 235, so the mass number of this guy must be 231. The atomic number on this side is 92, so over here, this must be 90, because 90 plus 2 gives us 92. And then we look at the periodic table. Number 90 is TH, which is thorium. And then it says beta decay of that. So we're going to take that thorium that just got made, and we're going to have some beta decay. What is the nuclear symbol here? It's the electron, right? So it's an E with 0 and -1. So the mass number is going to stay the same. It's still 231. The atomic number is going to go up to 92, and that's Pa. So that's the beta decay. And then it says another alpha decay. So this one then will undergo alpha decay. 231, 91. So alpha decay, you write your alpha particle over here. 231, so this must be 227. If you're bad with math, use your calculator. 91, so this must be 89. Periodic table says AC. Oh, and a plus sign. Okay? Write the nuclear equation for the positron emission of sodium-22. Okay, so sodium-22, that's its mass number. Atomic number is 11. So what's the symbol for a positron? It's like the electron, but positive, right? So it's got a +1 there. So again, the mass number stays the same, and the atomic number goes down, and we get neon. Write the nuclear equation for electron capture in Kr76. Well, Kr76, proton is 36. This is capturing an electron, so we're adding the electron. So this is gonna be 76, and this is gonna be 35. No. Wrong line. Okay,